Hello guys, and welcome to another calculus video. In this video, as you can see, we're going to be showing this awesome result that you can see right here. It's a little bit weird with the way that Windows shows this result, but this is just a big parentheses right here. We have that the integral from 0 to infinity of ln 1 plus x squared over t squared over cosh t dt is equal to 2 pi times this massive natural log with gamma functions on the inside. So you must be wondering, how did we get from the simple integral to this absolutely crazy result? And the answer is we didn't. In order to come up with this integral formula right here, I actually started with a very simple integral, and then I applied several transformations to it, turning it into a much more complicated, much more difficult to derive result. This is something that's sometimes known as integral milking. It's kind of a weird name, but it's just what people chose to go with. So if you type that into Google, you'll see the Stack Exchange post that inspired this integral right here, where they talk about how you can just take a simple formula and then apply transformations to it, and you can get into something like this. So let's discuss what you can do in integral milking. So integral milking is pretty straightforward. You just start with a simple formula, like for example, integral from 0 to 1 of x to the t dx is equal to 1 over t plus 1. And now, to both sides of the equation, there's a number of different operations we can do. One operation is we can integrate both sides. Another operation is we can differentiate both sides. These both fall under the Leibniz rule or Feynman integration, which we're all very familiar with. But there's a lot of other operations that we can do. We can multiply both sides by some function f of t. We can, which is not really helpful by itself, but once you apply another transformation, it might be a little bit more helpful. You can obviously multiply it by a constant, but that doesn't really do anything. The more important operations that are a little bit more interesting are, for example, we could sum it up from t equals 1 to infinity, or really t equals any number to any other number, and end up with a completely different result. In this case, it would just diverge, but if we slapped a negative 1 to the n on the front of there, we would end up with a different result, or negative 1 to the t, I guess. So you can, multiply by some function of t and then sum it from t equals 1 to infinity, t equals 0 to infinity, whatever you want. And so there's a lot of different things we can do, but the most interesting thing that we can actually do is use an integral transform. And the reason that integral transforms are so nice is because of the properties of integrals. We can interchange the outer and inner integrals, and essentially the integral transform will only affect the function of t that's inside the integral. So what I mean by this is, in this case, we could actually take the Laplace transform on both sides. And this isn't going to work out too nicely for us because this side doesn't have a simple Laplace transform, so it wouldn't really work out in this situation. But there are plenty of situations where this would work out and help us out a little bit. So we can do the Laplace transform. And another interesting one that we can do is we could do the Mellin transform, which is very similar to the Laplace transform. We're just using x to the s minus 1. And that's something that I haven't really covered much, but this one is also very helpful for integral milking if that's something you want to do. You can also take the inverse Laplace transform whenever you want to. I'm trying to think if there's anything else that's really all that useful. Nothing's coming to mind at all. I think this is all we're going to use in this video, but I absolutely welcome you guys to play around with common integral formulas and just repeatedly apply these operations. So don't just do one of these. Do several of these in a row to the point where it becomes hard if you look at the final formula to figure out what you did to get from the original formula. And that is a great way to create a really tough integral problem because you know how to solve it by peeling back the layers, but it might be hard to intuitively see the answer. So let's go ahead and look at my example that I showed you just a moment ago. Now there are two lemmas that we need for this, and luckily they're things that I've proved in past videos. So the first one is that the Laplace transform of hyperbolic secant of t is equal to, let's see if I can remember this, negative 1/2 digamma of s plus 1 over 4 plus 1/2 digamma of s plus 3 over 4. And another formula we're going to be using here is that the integral, this can be derived using contour integration. We're integrating cosine of ax over cosh of x dx from 0 to infinity, and this is going to give us pi over 2 times hyperbolic secant of a times pi over 2. Alright, so now we're all equipped. Let's go ahead and apply some transformations to both sides and figure out how we can milk this integral into a much more interesting formula. So we're going to start with this integral right here, and we're going to take the Laplace transform on both sides. Now, as I said before, the great thing about integral transforms, like the Laplace transform, is that we can interchange the integrals, and so essentially the Laplace transform of this integral is just the integral of the Laplace transform of this, and we're taking the Laplace transform with respect to a, so instead of t, we're using a. So what's going to happen when we do that? Well, the Laplace transform is pretty straightforward. We're going to get the integral from 0 to infinity of a, or I guess not a, or we're going to have s on the top here, s over x squared plus s squared times cosh of x dx. And using our rules of the Laplace transform combined with the lemma that we had on the previous page, this is just going to become negative 1/2 di gamma. Instead of s, we're going to have s over a, so that's 2s plus pi over 4 pi plus 1/2 di gamma 2s plus 3 pi all over 4 pi. Alright, so already we have a pretty magnificent formula here. If we just divide by s on both sides, we have a formula for hyperbolic secant of x multiplied by x squared plus s squared dx in terms of the di gamma function. And that's actually something that's pretty hard to show. I'm not actually certain of a way that you would be able to do it without this method right here. But this is just one step away from our original integral. So it's pretty easy to see that you could take the inverse Laplace transform to get back to the original integral. So let's make it a little bit more difficult. What we're going to do here is we're going to take all of this and we're going to integrate it from 0 to some variable v, and then all of it ds. And sorry, this integral sign should be over here. And what that's going to do, on the left side, we're going to have integral from 0 to v of s over x squared plus s squared ds, right? Which is just going to be 1/2 ln x squared plus s squared evaluated at v and 0, which is going to be equal to 1/2 ln x squared plus v squared minus ln x, which is the same as 1/2 ln 1 plus v squared over x squared. So that's what we're going to have on this side. On this side, we're going to have integral from 0 to infinity of 1/2 ln 1 plus v squared over x squared all over cosh of x. So already we have stuff with exponentials and stuff with natural logs, which we know is always a fun little pair, and something that would be very, very difficult to deal with. And now we have to integrate the other side. So reminder that the integral of di gamma of x dx is equal to the natural log of the gamma function. So this is going to be pretty straightforward. I'm just going to go ahead and do it, and you guys can check my work as we go if you like. I'm going to also multiply this 2 out and cancel it with these 1/2s over here so that we don't have to deal with that. So we're going to get 2 pi times gamma, or sorry, natural log of gamma of 2v plus pi over 4 pi. This is going to be a negative sign, plus natural log of gamma of 1/4 plus natural log of gamma of 2s plus, or 2v, sorry, plus 3 pi over 4 pi minus natural log of gamma of 3/4. And overall this looks pretty daunting, but we can just combine it all into one big natural log, and we have our result that we had just showed, at the beginning, which is 2 pi times the natural log of gamma 2v plus 3 pi over 4 pi times gamma of 1/4 over gamma 2v plus pi over 4 pi times gamma of 3/4. And so, what we have here is a magnificently complicated formula that looks incredibly hard to derive, but we just figured out this formula just from some very basic transformations and substitutions, and we have this right here. So this is one great example of what I like to call integral milking. Let me go, if you go ahead and change the variable names here, if you change the x to t and then v to x, you'll get what I had in the thumbnail. So integral milking is a really fun experience because you can get some crazy formulas that they're not necessarily super useful because you can't choose what formula you're going to create, but if you wanted to challenge your friends to a tough problem, this is a really, really easy way. I mean, I really just took like 20 minutes playing around with different functions and identities and formulas and was able to come up with this incredible formula right here. So, you can just take any old formula, apply the Laplace transform, and then sum it up, and then take the Mellon transform, and then take the inverse Laplace transform, whatever you want to do, and you'll end up with some awesome functions like this. So, I hope you guys enjoyed the video and the introduction to the idea of integral milking. And yeah, and go ahead and try out some integral milking for yourself. Come up with some crazy formulas and send them to me. And I'd love to try and reverse engineer what you did. So anyway, I hope you guys enjoyed the video, and I will see you next time.